Hey everyone. I think this is fourth video now. Is that right? Yeah, this is the fourth one. So last time we finally defined what a model is. And this time we're hoping to unpack and basically we've defined like we defined what a model is, and we're hoping to now build kind of a way to a calculation to determine truth, which is what it's this that you've probably done before, but it's more helpful to build the model and treat this as an actual object, and we'll see why as we progress. Why the slight reframing that model theory is so useful. Okay, so our goals. I laid this out at the end of the last video, but we have two goals for this video. So one, build a method of determining the validity of statements. And for number two, show that this method I don't know whether it works, or rather show that this method is correct is what I should say, right? Because it's kind of like an algorithm, but this is sort of the approach that we're going to take. So, and the way we're going to show the validity, and remember validity from last time, remember validity is this, right? Sentences that are true regardless of the model. Our hope is to build a method of determining validity of statements. Because, or I'll get to that, but our hope is to build a method that determines the validity of statements, and also show the proof that our method of determining the validity of statements actually works. Why is this important? Well, for instance, say that my set of sentence symbols S. This is just a quick argument of why what I'm about to do is vital. So suppose my set of sentence symbols is x1 ... xn ... So basically, I have an infinite set of sentence symbols. How do we know that, for instance, x1 or not x1 is valid? Okay, so how do we know that x1 or not x1 is valid? Let's take a naive approach to showing that this is valid. Well, what we would have to do? Well, of course, a statement is valid if it's true in all models. So we need to consider all models of S. But unfortunately, S is an infinite set. So considering all models of S, there's infinitely many models, right? There's infinitely many models. All infinitely many models of S. And that's not an approach that we can even do, right? We can't do that in finite time. So even though it's very clear to us that this sentence is true, and the reason it's true is it doesn't depend on the assignment of X, in order to check its validity, we would have to check it against all of the assignments of variables that don't matter, right? Of all of the x2, x3, x4, ... And that's not something we're going to do. So that's why this different approach is important. That we can, because, for instance, in math, right, all proofs ought to be finitary. Like, I can't give you a proof of something that's infinitely long. I need to be able to tell you if something's true or not in finite time. That's very vital, that I can, in finite time, tell you if a sentence is true or not. So we're going to find a way to determine the validity of sentences without having to consider the potentially infinitely many models in which this sentence is true. Okay, so this is going to be And we're going to do this with everyone's favorite thing, truth tables. So, we're going to formally construct them, though. I'm sure everyone's seen truth tables, but we're going to move forward. We're going to build them up formally so that we can actually use truth tables in proofs. Okay, so first off, a definition. Actually, I want to define this first. We're ultimately what we're doing is truth tables, but it's not going to look like that because I'm going to define it, formally. But we're going to talk first about an assignment. And an assignment is basically just a sequence A1, or how should I phrase this? So an assignment, considering S equal to x1 ... this could be infinite. An assignment is a sequence A1, A2 ... where AI equals T or AI equals F. Right? And so basically, intuitively, I'm going to tell you the value of each variable. I'm going to tell you if xi is true or if xi is false. And vitally, we won't talk too much about this. It's just important that this is the framework of. I'm going to begin by telling you which variables are true. So, and I used a word there that I did not define. Value. I said I would tell you the value of xi. So the next goal will be actually defining value, which intuitively this should be something not too unfamiliar. Intuitively, the value of a statement is just if it's true or if it's false. Okay, and we're going to define value, unfortunately, as we do everything, inductively, right? So hopefully at this point, actually this is a great time. So given an assignment, so I'll write this part at the start of this definition here. So the value of phi given some assignment A1 through AN and now I shouldn't say inductively, I should be saying recursively, actually. But so the value of phi given A1 through AN is, maybe take a moment here. So remember how we did, the first thing we did was we recursively defined the syntax of sentences. And then we recursively defined the modeling. We recursively defined that relation that tells us if a model, if a sentence is true in a model or if it's false in a model. So now, see if you can extend that to a definition of the value of phi given an assignment. And it's going to be, there's going to be 3 bullet points, and it's going to be exactly what you expect. Okay, so let's check to make sure that we understand what we're doing. So 1, if phi, and I know it's very repetitive, but it's good to get this down because it's nice that it's nice that this framework keeps repeating, because we'll be by the end of this we'll be masters of this. So if phi is some, and I'm now going to be using, since I have n many of them, I'm now going to be using xi. So if phi is a sentence symbol, the value of phi is a sub I, right? So we'll just, if phi happens to be a sentence symbol, we'll find the value, we'll find the assignment corresponding to that sentence symbol, and that will be the value of phi. Next, if phi is of the form not psi, the I don't know how to write, the value of phi is the opposite of psi. And then bullet point 3, if phi is psi and pi, phi is only true when psi and pi are true. Okay, so again, a recursive definition, and it's exactly what you think it is, right? Is that our base case of this recursion is that sentence symbols simply get the value of their assignment. And then for sentences that are built upon those sentence symbols, if we have a not, it negates the value of a sentence. And if we have a conjunction, the sentence is only true when both of the sentences forming the conjunction are true. Again, this is the definition that we've seen 1,000 times at this point. So maybe let's hope. Why are these three ideas different, right? So we had 3 things. We had syntax. We had syntax. We had, the model theory stuff, and then we had value. And why are each of these 3 things different definitions? Well, for one, these 2 things concern semantics, right? Model and the whole modeling definition and the whole value of a statement. The whole modeling idea and the whole value of a statement concerns whether or not the statement is true. So our first definition, basically the syntax one, the point of that one was to determine just if phi is even a sentence. And then the model one this is kind of the vital one. This one tells us if phi is true in a model. And then finally, the value definition has given us a way to compute validity. Okay, so I wanted to write this out so that we understand why this isn't like retreading old ground to define, almost provide the same definition 3 times. Each one has a different part. Why is this value one different? Well, importantly, I don't know if I'm going to be able to undo all the way. I doubt it. Yeah, okay. So if you go back to my old slide there, the one where I was talking about validity, you'll notice that I said the assignment was A1 through AN. And of course, this is a clear observation that since psi is necessarily finite, if you recall, when we defined a sentence, bullet point 4 told us that all sentences are finite. But since phi is necessarily finite, at most finitely many xi in S appear. So the model one sort of concerns these infinite objects, potentially infinite objects, A that represent every variable, whether it's true or not. But phi only needs to consider the assignments of the variables actually in phi. And that's why the model approach, does not give us a finite way of determining the validity of a sentence. But this value approach, this sort of much more syntactic value approach, will allow us. Okay, we're going to move forward now. This might be a little bit of a long one. So the next thing I wanted to do was introduce a new idea. We will say, and this is a single turnstile phi, we will say single turnstile phi if for all assignments A1 through AN, the value of phi is true. And remember, this is almost the same thing as the definition of validity from the last video, but this one is necessarily finite, right? And equivalently, we say phi is a tautology. Okay, so this is a new definition based off of this idea of value that we've introduced. So let's now say the big theorem that we've been trying to show. And this is actually called the Completeness Theorem. Or rather, it's kind of only part of it. The full completeness theorem will rely on things we haven't built yet. The full completeness theorem will rely on things we haven't built yet. But that will be the actually important one. But the statement of the completeness theorem is very simple. And it says just this. Okay, that's the completeness theorem. Or equivalently, right, for any sentence phi, phi is a tautology if and only if phi is valid. That's what this theorem states. So why don't you take a moment here to pause and try to just make sure that you're fully clear on what these two things mean: the single turnstile phi and the double turnstile phi. And as a result, what we might need to do to prove this statement. Okay. So, welcome back. Hopefully, it's just good to collect your thoughts on this. So, basically, we know that we've defined what these two things mean, and we're going to hope to show them equal. And of course, the one on the left was that notion, that recursive notion that we developed of value, and the one on the right was the idea of truth in a model, right? And we're going to relate them together. And the importance, again, from the very beginning of this video, the importance of this is that we can compute the thing on the left in finite time. And so this gives a method of computing the thing on the right in finite time. So let's begin, and we're going to write this down. We're going to finish it, and this will be the last thing we do in this video, but we're going to prove the completeness theorem, okay? All right. So this is the proof that we're going to do. So begin with a sentence phi. And now we're going to let x1, I don't like doing proof in red, actually. I'm trying to pick my color as well. So x1 through xn let x1 through xn be the sentence symbols appearing in phi. I haven't actually told you what it means for a sentence symbol to appear in phi. Of course, intuitively, phi is some logical formula, and a sentence symbol appears in phi if phi contains that sentence symbol. You could formally show, again, through that whole recursive definition, exactly what it means for a sentence symbol. This idea of what it means for a sentence symbol to appear in phi. Okay. So our approach to this proof from here forward will be constructing an assignment. So now, of course, we have a sentence, and I know this is something I get from the sentence, and we want to talk about models. So we're, of course, going to let a model. This is going to look weird. A model. And now for all of those xi that we developed earlier, let a sub I we're going to say a sub I is true if x sub I is in A, and of course, it's going to be false otherwise. So this is sort of the assignment that the model gives us. And remember, the model could be an infinite object, but the assignment I'm building is a finite object, right? So basically, we're going to prove a lemma. And the lemma is A models psi, if and only if phi, I should say phi, if and only if the value of phi on, I'm writing this really poorly, on a sub I, or a sub 1 through a sub n is true. Okay, so I know I did all that. Let's unpack exactly what I did. So I began with I'm going to begin with a sentence, and of course I'm going to enumerate all of the finitely many sentence symbols that appear in the sentence. And now I'm considering an arbitrary model. Okay, and then I'm building an assignment, sort of the assignment that the model tells me, right? So models contain sentence symbols, and we're saying intuitively, right? The whole time I've said intuitively a sentence symbol is in the model if that sentence symbol is true in the model. And we're now making that intuitive understanding of what a model is concrete. And we're saying build the assignment corresponding to that model by simply checking every x and assigning x true if it's in the model and assigning x false if it's not in the model. And now I want to show that the two notions are equivalent, so that A models phi, or A is a model of phi, if and only if phi's value on the assignment that A gives me is true. So I'm going to scroll down, actually, so I can keep that lemma on the screen. So that's the lemma we're going to try to prove. And of course, as you expect, actually, take a moment, see if you can prove this. It's very easy. And I'll give you a hint, it relies on induction. All right. So, of course, we're going to be doing a three-part induction. Exactly in a line with the one we've done. And if you saw the video 2.5, where I showed an example proof of induction using example proof of induction using our recursive definition, this is going to be very familiar. So if phi is xi, then clearly the value, I'm going to say the value of phi is true, but I'm going to actually, for the sake of brevity, write then phi is true. Clearly, if and only if AI is true, which is of course true if and only if xi was in A. And xi is in A if and only if A models phi. Okay, cool. So that's our base case. I'm going to write it out because these are going to be a little bit longer, so I'm going to write it out and then delete it. So that is, remember, the base case of the induction. So let's walk through this one more time to make sure that we're following everything, right? So if phi is just a sentence symbol, then the value of phi is true by, remember the definition of value, if phi happened to be a sentence symbol, it's true only if that sentence symbol is assigned to true. So that means AI must be true. And AI was true when we constructed the assignment based on the model. AI was true when X was in the model. And if X is in the model, then by the way we defined A modeling phi, we know A models phi. So that shows the if and only if in the base case. Now we're going to move into the two-case inductive step. So suppose phi is equal to not psi. Okay? So suppose phi is equal to not psi. And I may skim through this because it's so obvious, but maybe I'll do this one out fully. So phi is equal to not psi. So of course, by the inductive hypothesis, A models phi. Let's do this. A models phi if and only if the value, or if and only if the value of phi is true. But recall from our definitions that A, since A models phi, we know A models phi if and only if A does, do red for emphasis, A does not model phi. So I've been saying the wrong Greek letter. It gets confusing. So A models psi by definition of the model, right? By definition of what it means for A to model something. A models psi if and only if A doesn't model phi. And we also know that the value of phi is true if and only if psi is or I should say, just so that it's consistent with what I said above, that the value of phi is false if and only if psi is valued true. So finally, we see that, but we have that inductive hypothesis, and now we see that, this chain of if and only if, right? This is an if and only if, this is an if and only if, this is an if and only if, or this is an if and only if. So we conclude finally that this is an if and only if. And of course, so we've concluded that A doesn't model phi if and only if the value of phi is false. And by contrapositive, that means we conclude that A models psi, or A models phi if and only if the value of phi is true. All right. That's a good stopping point, actually. Well, no, I need to complete the proof. This is going to be a long one, and I'm sorry. So why don't you try out, remember the other case would be, suppose phi is of the form psi and pi. If you still haven't really followed these proofs by induction, it could be a good exercise to work out this case on your own. But the thing we'll conclude at the very end is, of course, that this lemma is true. Okay, so that was a very mechanical, sort of proof of that lemma. And yeah, that was a very mechanical proof of the lemma. And I'll rewrite the lemma briefly, that A models phi. A models phi if and only if phi is true on that assignment A1 through AN. And now we're going to see why this lemma, and this proof isn't very hard. They'll get harder later, but I may as well go through detail with it. Anyway, from this, let's now show why this lemma implies the global thing we're trying to recall. That the thing we're trying to prove is this: that psi is a tautology, or phi is a tautology exactly when phi is valid. That's what we're trying to prove. That's the goal of all this. Okay. So now, finally, suppose phi... actually, before I write this again, pause the video, see if you can figure out why that implication is true. Okay. So suppose phi, or I'll even write this out with my symbols that I've developed. So we're going to first suppose that phi is a tautology. So then let A be any model, and of course we're going to let A1 through AN the corresponding assignment. Of course, now, since phi is a tautology, we know phi is true on A1 through AN. Thus, by the lemma, A models phi. Since A was arbitrary, we conclude all models A model phi, and thus we conclude phi is valid. Hopefully that makes sense, and you guys are able to follow that. It's really just, all of this is really just unpacking the definitions, as proofs near the beginning of the development of a field of math tend to be. We're really just unpacking the definitions. So finally, last time, now we're going to suppose that phi is valid. And maybe at this point, I'll ask one more time. Pause the video and see if you understand, if you can see the reasoning why phi being valid implies that phi is a tautology. Okay. And it's, as you expect, it's almost exactly the same reasoning now. So suppose that phi is valid. We're going to basically just work backwards, is let A1 through AN be any assignment. Then let A just equal the set A1 through AN. This is a little different because we have to construct a model, right? So let A equal this. So A is going to equal just this set, and it doesn't it doesn't really matter the truth value of the variables that don't occur in phi. So we're not going to try to append to A other things. We're just going to say let A be the set, or rather, let me undo this because I'm writing this wrong. Then let A actually be this set. It's the set of xi such that ai is true. I've said that backwards. Okay, right. So it's A will be the collection of precisely the literals, right? Precisely the sentence symbols for which, it's exactly the sentence symbols assigned to true. Okay. Then, then first of all, obviously, since phi is a tautology, A models phi. So by lemma, phi is true on A1 through AN. And it's not too hard to look at and observe that. Remember, the whole idea was we would always take the model we begin with and produce an assignment corresponding to it. So I don't think it's actually that hard to see that. It's not too hard to see that the assignment that will be produced from A, because we defined A like this, will be precisely this assignment we began with. So, of course, by the lemma, phi is true, and thus we conclude phi is true on all assignments, and so that's the wrong one. Phi is valid. Sorry, phi is a tautology. Okay. So that concludes the proof. I don't think this proof is actually that bad. I know I went through it in detail. I prefer that. I'm sorry if this was a little slow. I know this was a pretty long video. In retrospect, I probably should have stopped the video when I started the proof and broken it into two parts. But I wanted to get through this also. Oh well, we've done it. So we have now shown. Let's backpedal out and just conclude with what we've shown. We have shown this statement. We have shown that phi is a tautology if and only if phi is valid. QED. And there's my box. Okay. So, next time, I'm going to do another one of those, like 0.5. I think this was 4. So the next video is going to be 4.5. And 4.5 will be really simple. It will just be an example of computing the value of phi. So anyway, that will be that'll be the next video. You feel free to skip that if you don't want to see that. I'm just going to be basically running through truth tables to ascertain that, that weird definition we gave earlier in the video of the value of phi is in fact exactly truth tables. Like what we've actually built is exactly truth tables, right? It's just a little bit more formal, and thus we can use it in proof. Okay, so anyway, thank you guys for watching. That will be 4.5, so I'll see you guys then. And if not, I will see you in 5, where we will begin discussing formal deduction and systems of proof. So thank you guys for watching, and I'll see you next time.